In this video, we'll talk about partial fraction decomposition with quadratic factors. So let's take a look at an example. We have x squared plus 2x plus 9 divided by x plus 2 times x squared plus 5. So we say that this fraction has a quadratic factor because notice in the denominator, x plus 2 is a linear factor, but x squared plus 5 is a quadratic factor because this x has a power of 2. So how can we decompose fractions that have quadratic factors in the denominator? Well, the form that we can use is some constant a over, if there is a linear term out here, we write that first. So there is a linear term x plus 2 right here. So we can write x plus 2 as the denominator for this first fraction. And then we say plus bx plus c over the quadratic factor. So the quadratic factor is x squared plus 5. So recall that when we decompose fractions like this, we want the numerator to have one power less than the denominator. So for example, the power of x squared plus 5 is 2. And the power up here in the numerator, bx plus c, we can imagine this x has a power of 1. So the numerator has a power that is 1 less than the denominator. So that's why we write bx plus c, as opposed to something like b or just c by itself, because that would be a constant with a power of 0. So keep that in mind. So once we have this format, how can we move on from here? Well, we want to clear the denominator from each fraction. So the way that we do that is we can multiply this entire expression by the common denominator, which would be x plus 2 times x squared plus 5. So notice that when we multiply this first fraction by this common denominator, this entire denominator will cancel out, and we'll just be left with x squared plus 2x plus 9. Now, when we multiply this fraction by the common denominator, the x plus 2's will cancel out, and we'll just be left with a times x squared plus 5. And then when we multiply this fraction by the common denominator, notice that the x squared plus 5's will cancel out, and we'll be left with bx plus c times x plus 2. Okay, so now we just need to FOIL this right-hand side. So let's write x squared plus 2x plus 9 is equal to, if we distribute this a, we get ax squared plus 5a. And then over here, if we FOIL these terms, we get plus bx squared plus, we have bx times 2, so 2 times bx, and then we have c times x, so plus cx, and then we have c times 2, or plus 2c. Okay, so now the trick is we want to try to group all of the x's together that have the same powers. So notice that there's an ax squared here and a bx squared here. So if we pulled out an x squared from those terms, we would be left with a plus b. And then notice we have a 2bx right here and a cx right here. So if we pulled out an x from those terms, we would have plus x times 2b plus c. And then notice that we're left with just the terms that have no x's, so 5a and 2c. So we'll write it like this, 5a plus 2c. So there's nothing to pull out there. So now the trick is we want to set whatever the value is within the parentheses equal to the coefficient that has the same x value on this left-hand side. So if we imagine that this x squared has a coefficient of 1, we would say that a plus b must be equal to 1. So here's how we can write that. A plus b is equal to 1. Now we can do the same thing with this next parenthesis. So 2b plus c, we're looking for the x on the left-hand side, and we're trying to set this 2b plus c equal to the coefficient for x. So the coefficient is at 2. So we'll say that 2b plus c must be equal to 2. 2b plus c is equal to 2. And then lastly, we have 5a plus 2c. Notice there's no x here, so we're going to set this expression equal to whatever the constant is on this left-hand side, which is a 9. So we'll say 5a plus 2c is equal to 9. So now we have a system of equations where we're trying to solve for a, b, and c. So let's make a little room here. Okay, so we have a few different ways that we can solve a system of equations. It looks like for this one it might make the most sense to use substitution. So that's where we solve for one of the variables and then plug it in to another variable. So for example, in this first equation, we can solve for a very easily by just moving this b to the right-hand side. So a would be equal to 1 minus b. Now what we can do is we can plug in this 1 minus b for a into this last equation. So if we do that, we get 5 times 1 minus b plus 2c is equal to 9. And if we distribute this 5, we can find that we get 5 minus 5b plus 2c is equal to 9. And we can move this 5 over to the right-hand side, so we can get negative 5b plus 2c is equal to 9 minus 5 is 4. Okay, so now we have negative 5b plus 2c is equal to 4. It looks like if we were to multiply this middle expression right here by a negative 2, we could get a negative 2c right here, and we could use elimination to combine that with this equation. So if we multiply this whole expression by negative 2, we get, let's write it over here, negative 4b minus 2c is equal to negative 4. So if we combine these two equations together, the c's would cancel out, and we would be left with a negative 5b plus a negative 4b, that's negative 9b, is equal to 4 minus 4 is 0. So we can see negative 9b is equal to 0. B must be equal to 0. So we've solved for one of our values. B is equal to 0. Now if we plug in b is equal to 0 for this equation up here, we have a plus 0 is equal to 1. So a is equal to 1. And notice if we plug in a value of b equals 0 into this second equation, we can solve for c. So we have 2 times 0 plus c is equal to 2. This becomes 0, and we can see that c is equal to 2. So we just solved for a, b, and c. So now we can write our final solution as a over x plus 2, so a we found is 1 over x plus 2, plus bx plus c over x squared plus 5. So we found that b is equal to 0, so there's actually nothing to write here, but c is equal to 2, so we'll be left with 2 over x squared plus 5. And that will be our final answer. So that is how we can decompose this original fraction into two fractions.